I'm not the only person to create an alternative periodic table, but it is the only one that attempts to integrate biological information with physical chemical information. Because I think we live in a hybrid world, as I said, and because of that, more than just biologists need to know about the materials. People like chemists and material scientists need to know about biological ramifications. So why am I introducing this? Because it may help you understand, how to do a material assessment. Also, I want to go into some detail about another invention of mine, a list of 130 social uses of materials. And as I said in the rubric for the MA assignment, you can choose a category, one of these 130 categories that inspires you. Like you may be really curious about laser generating materials, or you may be really curious about semiconductors or superconductors. And you can start with that inspiration, and then you'll find one particular material. But remember, the paper is reviewing one material. It's not reviewing a category, but this list of 130 categories may help you understand your interests. And as I said, use the 5 regions of the future as a guide to giving you a sense of which particular kinds of futures and systems you're really motivated to research about. Anyway, this is about both of these inventions, and this is a material assessment of patterns in the periodic table for the first one of what life is made of and what life is not made of. So there's a little zone in the periodic table where biological life fits, and the way it's currently organized, you can't really see that. But in this particular version, you can really see clearly where and why biological life is not made of all elements. Biological life is only made of a handful of elements. And I want to tell you chemically why. And that should be something you preserve because your body's made of those things. Anyway, moving on. And after this, then I'll talk a bit about the idea of 19 different things you can research in material assessment down the entire infrastructural pathway. And that's another rubric that I encourage you to look at. In your papers, you don't have to obviously research 19 different things, but it's a way to inspire you to think about the social intercession of all materials, that all materials will have these 19 different social connections, I'm arguing. And I'll get to that after this presentation. And then after that, I'll talk about some of my research about material assessment, about cotton versus wool in the textiles category. That when you choose a particular category, choose a particular material, you change the world. You really, there's a lot of UID, unintended, indirect, delayed effects of choosing any materials. And even something as innocuous as a textile has a lot of different ramifications. Why? Because as I said, materials are not abstract. Last time I said, every material is slightly biased in some way. And that biases the social, the political, economic world that we live in. So without further ado, let's look at the periodic table of the elements and then at the commodity ecology wheel. So now for the second point of this is the periodic table of life, or the periodic table of the healthy elements, and of course, the toxic ones. Back to the cover of our syllabus here, right? We live in a real world of hybrids where, we have biological specialists over here, physics specialists over here looking at their periodic table, sociologists that don't know anything typically about these things at all. But we live in a world outside school. School is not the world. The world is this hybrid place. And if you really want to be a good technical manager, you have to understand the interactions of the real world. And the real world, unfortunately, does not fit our academic world very well. And that's why this class exists, that's why technology assessment exists, because you had to add a technology assessment to a very kind of broken academic system that really doesn't teach you about the real world. It teaches you very small sections of the real world. But anyway, so I said, if we live in a hybrid world, why not have a hybrid periodic table? So previous periodic table charts only develop and exhibit knowledge from the physical scientists, right? So that's what it's for. But if we don't live in a physical world, we live in this hybrid world. So I wanted to develop a better periodic table that will tell physics and chemists what, every day they would see that. It's very important. Going back to Heberlein, this will be a cognitive fix, right? Cognitive fixes, Heberlein said, are very cheap. So I see the periodic table of life as a very cheap cognitive fix for a lot of very bad material decisions. Anyway, I want to develop this better periodic table that gives us a better material assessment of what is good for us and what is bad for us by definition, and then build our world and education from better interscientific knowledge of the better applied choices of materials, of what is good for life instead of bad for life. There have been many suggestions for an alternative periodic table of the elements, though mine is the first hybrid one to updated element information showing inductive oddities. I mean, there's some weird things about the elements that can't really fit in only one little box, and I want to show you that on this chart. So there's really chemical and physical updates in the chart by itself, but also it shows health information. And if you just go to any search engine and type in periodic table alternative, search for images, you'll see bizarre things that are very hard to remember. So I looked at a lot of these and I thought, these are terrible ideas because nobody wants to look at these ugly charts. So I tried to make a chart that's kind of pretty and simple enough that will lure you in as well, but has a lot of complex information. That's, there's bizarre things that are not very useful, I think. They're very interesting, but they may carry particular value by showing different kinds of patterns, but they're really hard to remember like this if you're looking for something with periodic value. But anyway, remember this. How many of you know the European folktale about Goldilocks? Anybody? Just type in the chat if you've ever heard about that. No. Goldilocks and the Three Bears. Yeah. No. Okay. Goldilocks is eating juke, what it's actually porridge, but it's European juke. And she went into the house of three bears, and one was too hot, and the bears weren't there, obviously, and the other one was too cold, but the other one was just right. So the Goldilocks idea is used in thinking about life on Earth. Like, our planet is in the just right category. It's not too hot like Mercury or Venus. It's not too cold like Mars or other distant planets. It's just right in the middle to support a very stable life, to support liquid water, whereas liquid water is in vapor only in other places closer to the sun, and it's frozen into ice in other places. So we're in a special just right zone. But I think in the periodic table for life, there's a double Goldilocks zone. And I will talk about that right now. That means life is chemically built only of the overlap of two just right zones. Yet our modern supply side world of industry and militarized world is full of short-term choices of chemical extremes. The military has a mission, it achieves the missions the fastest way possible, not always the safest and cleanest way. Same for a lot of people that want to make quick money and they don't think about long-term ramifications. That's for the lawyers and the poor children that grow up with birth defects. That's for them to worry about, right? So a lot of very selfish people play with materials for their own benefits and not for the long-term interest of our whole species. So I think it's time to redesign the materials of the world to be safe for everybody. It starts with a more systems view of biology on the periodic table. And this is my chart, and I will explain this in detail in just a moment. But what are the double Goldilocks? Number one, things that are too small, things that are too big. Remember, on the current periodic table, all the boxes are the same, right? It looks like every element has the same space, but that's not true. And I think in future updates, you have to make hydrogen really small, and you have to make, xenon, cesium really big. So in this chart, these get bigger as it gets out of that. So the smaller physical blocks sort of really mean smaller physical elements, and that's true. And that's very important for chemical reactivity. This small and large, and life is just right in the middle, but small and large is shown in this chart. You have much smaller blocks and much larger blocks toward the outside. It also helps explain why things are so chemically reactive, like fluorine. Here's fluorine, right close to the middle. So it's physically smaller. It only has, how many? Nine protons. So that's why fluorine acids are the most dangerous, because they're the smallest physically. That means fluorine is smaller. It will get into a relationship and break up other things. If fluorine was bigger, it couldn't do that. That's why hydrogen is the basis of all acids. It's not because hydrogen, it's because hydrogen is small. So there's really a physical size that should be shown on all periodic tables that hasn't been shown before. And I can improve this one to make it, you know, a bit better, but this is a first draft per se. So I think life is just right in the middle. All of life is right here, over here in this little zone, below the green line, but above hydrogen. So it's all, life is basically filled of all these things with percentages. This is your body. All these percentages of what your body's made of. It's also made of water mostly, which is your hydrogen and oxygen. So our body is really this, with the tiny amounts of dust of all these dots. There's sodium, there's potassium, there's calcium, selenium. These are all trace elements. Some of them are toxic, that are black, that can be dangerous, but others, like with a tiny dot, iron, they are magnesium, chromium. In small amounts, these are part of your body. So we really are creatures of water with tiny amounts of upper elements floating around in it that facilitate chemical reactions. But mostly the infrastructure of life is this tiny little zone in the yellow right here. And I'll explain what the pink equal sign means in a minute. That's just one of the principles. So life is just right in the middle between things that are too small, like hydrogen, and too big, like radioactive elements, right? So life is in the middle physically, the size. The second Goldilocks principle is between things that are too electronegative and things that are too electropositive. Why is that important? Because if it's too electronegative, you get things like chlorine gas, you get bromium, you get fluorine. These are terribly corrosive things. And so you can't build life. Those are destructive. And this is, in this chart, instead of being on the far right, all of the noble gases are in the middle because they're neutral. I put the noble gases in the middle because I think they're neutral. They should be in the middle, and the most extreme things are on each side. So you have all the high negativity things on the left of the noble gases and all the high positivity things directly to the right, and things swirl around like that. And this explains why, you know, the transition elements have so many valences, because it doesn't really matter. It depends on the situation. So the further you get away from these extremes, all of these things at the top part of this chart, they have so many different ways of combining. And that's why most of the chart doesn't really, the current chart doesn't really make sense, because most of the chart doesn't fall very clearly into certain columns. And that's just a principle of reality, that the chart predicts all these predictable realities, but that only works on the edges. In the middle of the chart, the whole chart makes no sense because it doesn't follow valences anymore. It's all depending on more chemical reactions. And that this chart explains that, I think, very clearly. But anyway, once again, life is not too electronegative, life is not too electropositive, it's just right. It avoids the most ionic positive elements, which are like lithium. These you know, sodium by itself will blow up too, even though you need it as a trace element. Life prefers predictable covalent bonds. Covalent bonds are bonds that lock for life. They, you know, if you're passed by with another chemical, the elements don't reach out and grab that one. They're really locked because they're sharing electrons. They're not just associated on the surface with an ionic bond. There's two kinds of chemical bonds, ionic and covalent. But all of life, carbon is covalent. Nitrogen, oxygen, you know, potassium, sulfur, some degree chlorine, carbon, all of those make covalent bonds. And that's what biological life ended up being made of, stable relationships. You can't have life if, you know, accidentally you pass a hydrogen atom and your whole body falls apart. So we're made with covalent bonds, and that's really indicated clearly here why that's so. So the two double Goldilocks principle, too small or too big, we're just right in the middle of the size of the elements. Too electronegative, too electropositive, just right in the middle. Slightly electronegative, but making very stable bonds. Other details of this chart, it integrates much of the work of others' critiques of the other periodic tables. I've shopped around and used Photoshop for a periodic table diagram that I consider having some very useful features. And I'm basing this one off by a man named Muhammad Abu Bakr of Hyderabad, India. Upon the Abu Bakr table, I added more information. So I've added the colors, symbols, percentages, organization, and even changed the orientation, because I think that his Abu Bakr's chart can indicate a lot more things than he thought The periodic table, though, is arranged for more interscientific assessment instead of just arranged for chemists or physicists. It's for social scientists, biologists, chemists, and physicists combined. It has data summarizing many different layers of biological safety and toxicity about chemical elements and the health of the human species. Though I started my career in chemistry, I increasingly worried that chemists seem mostly uninterested in what later would be called green chemistry. Green chemistry is how to stress clean and safe chemical relations instead of just to experiment with a wider world of toxics for their employers in companies or states, with the ultimate damage to us or life in general. So really, this is a scientific chart, but it's also a moral chart. It's a moral chart of what you should be doing and what you should not be doing. And there's really, I'm not going to go over these in detail, but there's 19 things that are really integrated in this chart. I'll just quickly go over these, and I'll put this PowerPoint online in the cloud drive for you to look at for later. But the trace elements, as I said, are all on the dots per se. But one of the features is a double Goldilocks principle. Biological life develops only when it can be stable and predictable chemically. Life doesn't happen with ionic bonds. Life is really based upon stable, predictable covalent bonds. So biological life more naturally develops its infrastructures among predictable and stable bonds, or the most predictable and stable ways of breaking and forming. These are biological life's evolutionary choices of materials and show that biological life is created and is held in suspension in this infrastructure of a very small number of elemental choices by that double Goldilocks principle. The first just right window, which we talked about, the middle zone, reading left and right on that chart. On left and right, we have 2 electronegative, 2 electropositive. Just right is in this little zone here, per se. Moving on, the second window, mostly in the middle circles when we read the chart from the center to the outside. So if you read from the center to the outside, you have hydrogen to this outside. The physicality of elements are too small. They intrude and wedge into everything and screw it up as they get smaller, and they get unpredictable in valence. So they get far more unpredictable as you move out, and you can't build life on that. So that's the dynamic there. It's high time that after 100 years to play with the elements more knowledgeably for the window of life and health. Other points that I'm not going to go into, I note where the covalent bonds are for elements. And that's shown here by the equal sign. That's all the covalent bonding that happens in the periodic table. That's it. There's no other place. And that's exactly where life is. And where the ionic bonds are. Diamonds tend to be ionic bonds. These little pink diamonds are ion. You see a lot of ionic bonds here, per se. But nonetheless, as I said, it's updated physical information to the idea of a doubled aluminum. If you notice, aluminum is in 2 places on this chart. That's not weird. That's really the way aluminum works. It really fits in 2 rows. And there's an argument for that. You could read from Habishi's idea that aluminum really is an interesting element per se. Helium is really opposite the rest of the noble gases intentionally, because helium is not like the other noble gases. It's really a unique thing. If you read about helium, it has very different properties than all the other noble gases. So I think it deserves its close association with more of the hydrogen. But on the current periodic table, they're separated so far apart. You'd never really think that they're very similar, but they're quite similar. And this chart shows you why they're similar. Other things, 3 electrical locations of hydrogen. This is true. Hydrogen is not just one place. Hydrogen really has 3 valences and deserves to be located in 3 places. It's so small, it can do so many things, and that's why it's unique per se. Nonetheless, small black dots are toxic elements. You can see some of those here. This is not exhaustive, but lithium, beryllium, other things, cadmium, mercury, all those things that we know, all of these polonium, bismuth, lead, tellurium, those are quite toxic. But the other dots are different trace elements. Green dots are the trace elements in the yellow row. Yellow dots are the elements of life in the green row. So all those other dots that you see, like these green dots, we're slightly built of those, but it's just in tiny trace amounts, never as an infrastructure. They're really catalysts for chemical reactions, mostly. the lanthanides and actinides are off to one side. They're really an odd thing. So they're really off on the side. They're not a base of the periodic table. The current periodic table looks like that's so important, but they're so small and they're mostly radioactive and they all fit here. Like this is lanthanides and actinides. This is really where they go. They're extensions of this strange zone. And if you saw those odd periodic tables earlier, that's why there's that strange leg on some people's periodic table, because there's a weird effect of electron shells at that level, and they all get filled up slowly and then they move on. And so it's really the effect of electron shells at that level that makes very odd elements right there. Shading and fading of colors, I could do that a bit better, but I would like to make these a bit darker in the middle and make all these a bit lighter. And they're not as light as I'd like to make them, but that's the point, that you get a stronger reactive colors in the middle and very weak and unpredictable things toward the outside. Maybe even moving all the way towards white and no color on the outside would be a way to show that. But this is draft in progress. I'm not going to all these other things. You can look at all that, but there's a lot of things that explore, I think, the periodic table a bit better here. And we'll move forward ahead about the commodity wheel. This is a bit shorter. And this is a list that I've assembled over a long period of time, perhaps 20 years. And this was the basis for my recent National Science Foundation grant dealing with how do we build a circular economy. You may wonder, why is the earth in the middle? Well, every material category gets its materials from the earth and dumps things on the earth. So, this category of textiles may dump its waste on the earth, and maybe those wastes might be useful for another category. So the earth is not just there to be cute or be a symbol. It's really because it's the center of all of these categories, and we need to take care of the flow of all the materials among each other. And this chart is kind of a planning diagram. It makes you think about which categories you think are important to link together in more circular flows in the economy. So you may have seen, let's use an analogy, what this is. Vitruvian Man. You may have seen this image, but didn't know it was called Vitruvian Man. It shows the balance and proportions of all of our bodies, where you have the body drawn by Leonardo da Vinci, it's with his arms outstretched and the legs outstretched. This is the Vitruvian Man, drawn on paper in 1490. Printed books just started to be developed and cheap paper started to be developed. So a lot of people were making notes, and he was one of the most, he had huge numbers of waste paper and just notebooks and notebooks of notes. And this is one of his notes. He noticed the human body has a nice proportion. It was right for the human body in isolation. So this is the way human body looks. Yet you and I are not isolated. You and I depend on water. We depend on housing. So our body really is our choices of our environment too. And that is our bigger body. That's what I call our networked body. So this is just our biological body, but this periodic, the commodity wheel that I showed you is really our networked body. And therefore we choose to create an ecologically balanced or unbalanced network of ourselves around our lives. And so if this is the commodity wheel, that's our networked body. We make choices, 130 choices every day. Or if you don't make them, somebody's made that choice for you. And that's the image of all our choices that we have invented, that are extensions of our human actions and desires. That's really the first image of our networked body, to include our extended material choices. That's our extended body, really. Your connection to semiconductors, your connection to electrical connections and materials, your connection to textiles. Leonardo drew a man totally naked. We're not walking around totally naked. We walk around in particular choices of clothing, particular choices of shoes, particular kinds of food. Those things are important. So what I did, if you think about this Vitruvian Man, this is what I'm thinking that is a good image of the human species. If you put Leonardo da Vinci's image together with the commodity wheel, this is our extended body. This is an image of all of our choices that we have invented that are extensions of our human actions. It's the first image of our network body, to include our extended material and technology choices. That's our extended material body, really. And it's the image of the true human body, because we're not walking around naked. either for godlike good, we can make good choices, or for Shiva-like destruction. Shiva is the goddess of destruction and death in Indian divinity. But the point is, we decide, we make decisions like that about all the materials around us. They are not neutral, they are decisions. And with decisions come moral value or immoral use. So the point is, I want to close on this story right here of the Native American story of the two wolves. And our network body is like this story of the two wolves. And I've adapted this to discuss with commodities. You can read the original one here if you want, called The Wolves Within. It's a Cherokee legend. Cherokee is one of the Native American tribes of the United States. So an old grandfather is teaching his grandson about life. And he says, "A fight is going on inside me," he said to the boy. "It's between two wolves. One is good and does no harm to himself or anything else. He has humility, kindness, benevolence, and empathy and compassion. And because of this, he lives in harmony with all around him. Because of that, he easily acts and thinks in the long term as he sees clearly how others and all nature is a web around him and is part of himself. He will only fight when it's right to do so, in the right way. However," the grandfather said, "the other wolf in me is evil. He does harm to himself. And everything else around him, his arrogance, superiority, ego, greed are so great that he fights everyone and nature all the time without thought of repercussions. Because of that, he never acts or thinks in the long term, and thus is without harmony in himself or in everything around him." And the grandfather looked at the child and said, "The same fight is going on in you and inside every other person." And the grandson thought about that a minute, and he asked his grandfather, "Which wolf will win?" "The one you feed will win." And so one harms itself in the environment by its choices, and one develops itself by its choices. And which wolf will win? The one you feed. Which choices you make in life is really the wolf you feed, the one we feed. The common ecology diagram helps us feed the good wolf, and it helps us create the good network body around us that helps that. And so the point is, by our poor material technical choices, we've created a lot of great evil in the world right now. We're creating the world's 6th great mass extinction, and this is the anthropogenic extinction. Biological life has gone through 5 other mass extinctions, but humans had nothing to do with those. But only in the past 200 years or so. It's a combination of all these things I list here: biodiversity loss, pollution, all these are choices. Also social diversity loss. There's globalized systems with very little cultural variety around the world. That's the arising idea of local tech, that there's something valuable about locality and not just only globality. But the mechanisms about this are, we'll learn in this class about plankton or plastic in the ocean, biodiversity loss, wider species diversity loss, bioaccumulating toxic chemicals in parts per million and parts per billion, microwave radiation, EMF is electromagnetic frequencies, infertility comes around from all of these things, child cancers are on the rise, inherited genetic damages are on the rise, our soil becomes toxic, our food becomes toxic, and creates a terrible vicious cycle. Those are choices, or toxic choices in our network body around us. We may overcome this. In fact, we are living in a very optimistic time regardless, because I think we are really the first civilization that's working on fixing this. Previous civilizations, they didn't really work hard on that. They kind of fell apart as they ended up that way. But on the one hand, we may go extinct because many species of mammals have gone extinct. But however, as I said, we're the first civilization really to also be concerned about designing a better networked body around us. And I think that's very positive. This is just the beginning that's been started in the past 20 or 30 years, really. So the point is, we may escape this, and we may learn to fix our ways and to make more biodiverse and ecological civilization. And that's what I work for. I feed the good wolf, so to speak. But anyway, by our good material technical choices, we are already beginning to create a great good. We are creating solutions to everything in the past 30 years. Many of them are not really applied, but they exist. There's a lot of very good ideas and solutions for everything now. And that's one of the purposes of my grant. I wanted to basically tell the world, like, don't be depressed. I mean, there's a huge number of good things. You just have to be more aware of them and to have a positive image of the future. And if you don't, like, go back to Pollack, if you don't have a positive image of the future, you get that negative image. So you have to help invent that positive image for people. That's very crucial for motivating people to do good. Anyway, so we are creating solutions for plastic in the ocean. We are creating for ways to expand instead of demote biodiversity, to maintain wider species. We are creating many technical fixes for remediation. We can remove a lot of chemicals from our bodies now and other animals and the soil. We are finding other ways to cook food quickly and easily without microwaves, which actually destroy nutritional information. I mean, read about it. If you microwave a lot of food, you're basically destroying its nutritional content. And this has been known for about 40 years, but the microwave industry doesn't like to talk about that. We are discovering causes of infertility and all of these things and solving these. We're creating a more soil creating society and not a soil destroying society by reinventing agriculture into what's called agroecology, using ecological systems to make agriculture. Ways to create clean water beyond filling it with chlorine. Chlorine, is used in most of the world's water systems, but it's a slow dose poison. I mean, basically it's a neurotoxin and it's carcinogenic. It's not a good choice. It's a cheap choice, but it's not a good choice to fill your body with chlorine every day. So, which is really bleach. So there are better ways to clean your water systems than to use chemical fixes like that. We can overcome this by choosing to overcome, and the choice is yours and ours. So which wolf will you feed? That's my question to you. Prolegomena, this means just preliminary ideas about, think about an infrastructure in our lives. So materials is not just something you buy and throw away, but has a long series of social locations. And I want to show that too. So it's a cross-cultural way to analyze politics and all the flows of materials. But the summary, I want to give you 19 positions to analyze in any material flow of social relations. And these are 19 are all social political decisions, just like the network body or 130 decisions. These are 19 decisions that make the materials in your life. Drawn from more comparative study, this is something politically infrastructural to all commodities and all experience behavior. All materials have forms of this political power, whether hegemonic. Hegemonic means dominant culturally, or subaltern. Subaltern means sort of powerful, but not widely, agreed to. The vocabulary is suggested to capture this infrastructural political economics. And I'll just skip forward to some images here. Here's some examples of infrastructures. I mean, here's a Supertech, Supertech solar, right? This is a Supertech solar version. So it's a massive, expensive thing, size of people here. This is on a large building. We kind of have Supertech solar on our campus in the circular building on campus. But here is the same energy, but on a local tech version. So when you think about a particular choice of materials or energy, you can have big energy or small energy. And these are very different ways of thinking about infrastructures, but they're still the same technology, but they're used for different social purposes. Here's the oil, like the other one is all about oil. These other three pictures are all the oil infrastructure. On one side is a man, he's very happy with his Peugeot car. He did a very good job making the Peugeot icon with his hands. It's a lion on the front of the car, but when, it's choosing your car is not the only reason. When you're connected to the car, you're connected in your identity, and you may love the aesthetics, but you're connected to this long stream of oil, and that oil goes through global oceans to get to you. And sometimes this is a tanker that split open and sank, called the Prestige, I think off Spain about 15 years ago. But you depend on oil being transshipped to you globally, sometimes from countries that are very repressive to people, like Middle Eastern countries. So here's a Middle Eastern Arab feeding the world oil and getting money from the process. So all these three people may not think they're connected, but they're tightly connected in this one flow. And this person here with the solar laptop may not think he's connected, but they're all connected, probably the same manufacturer. So just different infrastructures. Here's another political side. This is a joke image. This was not, Texaco is an American oil company, but this really did say the Ministry of Oil. This is in Iraq. United States invaded Iraq in 2003. And the first thing they did was to go to the oil ministry, because that's the center of the wealth, and they took over the oil wells that way. And so really, taking over Iraq was really taking over the oil infrastructure and connecting that. Let me skip forward to those 19 points. That's all I want to talk about today. Here we go. In order from extraction to waste, that's how you can think about the flow. In your paper, I want you to think, aluminum, where does it come from? Or if you choose lead, where does it come from? Where is it extracted from? That's part of the story of lead. If you just want to choose hydrogen, where does hydrogen come from? This, how do we get it? How do we isolate it? And then waste, where does waste aluminum go? Where does waste lead go? These are very important things you need to know if you're going to make a material assessment. And my argument is the same path of 19 positions can help explain what kind of data you should look for. So all those 130 different use positions I showed you earlier in the commodity wheel, all of those have each of these 19 different points. And each of these points are potential political vetoes or other challengers. For instance, like extracting aluminum. What do I mean political veto? That means aluminum is extracted around the world, but maybe, several countries refuse to sell their aluminum. That changes decisions elsewhere around the world too. So that's what I mean. These 19 points have to line up to make the materials flow. And a lot of people will lose a lot of political power and even invasions to keep them flowing. But anyway, here's the 19 points. Pre-choice, you don't always know where the materials are. So you need to do research. So that's really, research about choices. That happens as part of any material regime. And then the original choice from the raw material set, competition from other choices. Like what are the immediate competitors? If you choose aluminum, what are the other places to extract aluminum? Why did you choose this particular location to extract aluminum and not the other location? All those things really matter. Why did you choose aluminum versus steel? Those are the kind of pre-choice issues. Other extraction sites, is another pre-choice issue, as I said. Royalties, you want to make sure you extract aluminum from a country that has low royalties, maybe. Maybe you don't want to extract aluminum from a country with high taxes. So you try to make a deal with the government to lower your taxes. That's what I mean, that this flow is really a social and political thing. It's not just an economic thing. It's very strongly economic thing, but prices get set by political taxes and laws and things like that, as well as wars. So in other words, labor, you need to have a lot of labor. What if you find a lot of aluminum? What if the country says, okay, we're not going to tax you, you can mine our aluminum, but the aluminum is in the middle of a desert. There's no labor in the middle of a desert. So you have to bring in a lot of labor, you have to build a city for the laborers. Maybe that's too costly. Maybe there's another country that they have a little royalties, right? But they have a huge population. And so he said, well, if we choose the country with a little royalties, but they already have the labor there and they're poor, so they're more likely to work in our mining industry. So a lot of these values are, that's very important where labor is in the whole scheme of things about materials. Financing, where do you get your money? Is the government going to help you? Are you going to self-finance it? Is the World Bank going to fund it? All these things matter about as well. Sometimes financing can be withdrawn, and that will change the whole location of where materials come from. Sometimes labor relations totally change, and that will change really everything about where materials come from. Transportation, how easy it is to transport things. That's very important. You don't want to drag something out of the middle of the Amazon. You want to be sure that it's easily connected to the oceans. So maybe Brazil gives you a good deal. Maybe Brazil lowers its tax rate for you, but Brazil says you have to get the materials from the middle of the Amazon to the coast. And you say, that's very expensive because Amazon floods and is dry. It's very hard to have a stable flow of materials. But maybe you go to Nigeria. Nigeria says, oh, we have a lot of aluminum right on the coast will tax you a bit, but you can build your own port right next to the ocean, and you could take your aluminum out very quickly. So you might choose Nigeria over Brazil, even if Brazil gives you better financing, simply because of transportation. Appropriate tariff barriers, I talked about that. Taxation on shipments, all of these things can interrupt or continue to make the materials flow. Manufacturing and refining, how easy that is to do in the target country or not. Marketing and advertising, all of these things matter. Taxation on items, transportation, competition from others, consumption, consumer consumption, waste disposal, and medicine, like how do you deal with the toxic effects? Now, these two things, number 11 and 14, number 11 and 17, supply and demand, those are typically all economists talk about. That's a very limited view of materials. Materials really have 19 social places, and you're being limited in your thinking if you think there's only two important things. And a lot of things can change manufacturing. A lot of other things can change consumer consumption. All of these other things can matter.